All right, let's slowly get going. Probably we'll see. Maybe someone else will join. Right. So welcome everyone for this first practical session for this mass refresher course. My name is Evgeniya. I will be teaching practical sessions. We'll have I think something like 8 or 9 of them once a week on Mondays, if nothing changes. And as far as I know, the lectures you have on Thursday, so you'll have weekend or extended weekend to kind of digest everything you learn during the lecture, and then during these sessions we will go over maybe some questions that you have, and also do some practical exercises, maybe see some topics in more detail. We'll also have we'll have both kind of pen and paper exercises, but also Python exercises. So that's we practice everything. If you're not very familiar with Python, then you get additional practice. You have opportunity to learn it. If not, then you'll just hopefully do some interesting math-related stuff with it. All right. Let me know maybe where you located. It's interesting to know, since the program is international. People are very often all over the world. You can write it in chat or just say it, right? I can start. I am based in Prague, in the Czech Republic. What about you guys? Yeah. Good. Seminarist. Good.
Hello, this is
Hey.
Mudassar. First of all, really thanks for this opportunity. Actually, I am based in Dubai, but due to my job nature, I am traveling. And right now I am in China, in Shanghai. It's like midnight here. It's
Yeah.
it's
Thank you.
little.
I wanted to say, it's impressive. Thanks for joining. Yeah. Great.
It's little hectic.
Yeah.
Yeah, thank you.
Yeah, I can imagine. Yeah, I was once teaching your course, and it was during COVID, so everything was online, and people went. It was also European time, but everyone went to their home countries, and there was one student who was on Cuba, and we had
Right.
an exam. It was the best student of the class, and we had an exam, and
Wow.
the class was at 9 a.m. right, and well, European time, right, and then I see that everyone submitted, but he didn't, right, and I was very surprised because it's like he was the best throughout the course, right, and I was kind of pinging him like, what happened, and then he was like, sorry, I fell asleep, because it was like 3 a.m. there. So yeah, it's a time difference. Interesting. All right.
Yeah. Thank you.
Good. Right. So let's see. If you attended the lectures, well, the lecture, yeah, the one that you had, then you know that the first one, we started hopefully nice and somewhat easy. You discussed some basic concepts from linear algebra, right? You talked about vectors. You probably discussed dot products between vectors, dot products, norms of the vectors, and then there were also hyperplanes, right? Also angle between vectors. Right, and this is pretty much all the topics that you've covered, as far as I remember. And for today, what I've prepared for you is first just to refresh these basic concepts. We'll do a short quiz, not graded, not so no reasons to stress. A very short, easy quiz that will help you to remember all of this. And then we'll see if there are some questions that seem problematic. Then we'll discuss them all together, right, to eliminate any doubt. And then we'll do a couple of Python exercises on on these topics, basically on vectors and hyperplanes, right? Right, so this is our plan for today, and I hope we'll be done in like an hour and a half, right? That's the standard length of the class. Right, so I will join you. I will send you a link to the Google form. You can now see it in chat. So that's a link to the quiz based on the first lecture. Let me know if you have any issues opening it. But if you can access it, then let's spend maybe at most 10 minutes working on it individually. And then in 10 minutes, I'll see if some questions were, if there were some doubts, we will discuss the questions, okay? So let's now work on this quiz, right? This is how it looks like, right? Once again, it's not graded, not gonna be recorded, so just yeah, try to do your best to check your understanding, all right? And once you're done, just click on submit, and then I'll see your submission when we're all done. We'll discuss, but let's not spend more than 10 minutes on it. Right, I see that one of you already submitted the questions. Sorry, the answers. Let's wait for maybe 2 more minutes for the rest to do the same. So please click submit so that we can see if there are any questions. Okay. We are 6 people and 2 of you submitted right now. So please finish answering the quiz. Okay, let's see. I have 4 responses. Would be great if we get 2 more, but let's see. So most of you did something around 4 out of 6. Was 1 person who answered everything correctly. And the forum tells us that the most challenging question was the one with the correct statements about some vectors. So let's take a look at that one to eliminate any doubt. All right. Let me just copy it and we'll discuss. This is the one. Let's see. Okay. Let's discuss this one since it was frequently missed. Right, let's just go over all the statements and discuss if they're true or not and why. The first statement says that vectors u and v are orthogonal. Is that true or not, and why? How can we check? What does it mean that the vectors are orthogonal to begin with? Yeah, Max says in chat that vectors are orthogonal if the dot product is 0. That is correct. Right, that's the easiest way of checking this. And what is the dot product between vectors u and v? Is it 0 in this case or not? Yeah, Dasha says it's -4, so it will be 1 times 0 plus 0 times 1, -2 times 1, and 2 times -1. So it's -4, right? Which is not 0. So the vectors are not orthogonal. All right. So this first statement is incorrect. The second statement, vectors u and v are orthonormal. Okay. Since they're not orthogonal, then they are also not orthonormal, right? But just to make sure that we know what that means, when are vectors called orthonormal? Which two conditions should be met for a set of vectors to be orthonormal? Anyone remember? Yeah, orthogonal. Yeah, Max says in the chat, the vectors should be orthogonal, pairwise orthogonal, and their length or the norm of each of the vectors should be 1, right? So they should be unit vectors, right? In this case, none of these conditions are met. So the vectors u and v are not orthonormal. Great. Then there is a simple vector equation, right? The statement is that vector u can be represented as -2 vectors v plus vector w, where w is this vector. Is that true or not? Let's see. -2v, that would be 0, -2, -2, 2, plus w, which is 1, 2, 0, 0. And what we get is 1, 0, -2, 2. And this is exactly vector u. So this is indeed true. Finally, the first true sentence. Okay, let me mark this as.
Can I ask the stupid
Sure.
question?
Sure.
So how we get 0 and -2, -2, and 2?
Let me see, maybe we don't get it. Maybe I made a mistake. So it's -2 times vector v, right? And it means that we need to multiply every. Oh yeah, that's true. That's I think I made a mistake, right? We need to multiply every component of vector v by -2. Okay, let's see if I made a mistake or not,
No,
right? So it's -2
You're right.
times. But I'll just finish it just to yeah, for completeness, right? And then so it's -2 times this vector, and then if I multiply every component by -2, -2 times 0 is 0, then it's -2, -2, 2.
Yes, thank you.
Yeah. You're welcome. Good. So that is correct. Now, the next statement, vector u is longer than vector v, right? To answer this question, we need to remember what is the length. What do we mean by the length of the vector? Right? How do we compute the length of the vector? Yeah. So the length of the vector, if nothing nothing else is specified, right? Generally, what is meant is that we use the L2 norm of the vector, and the length is the square root of the norm of the vector, right? So since we need to compare two lengths of vectors u and v, right, we can just compare their L2 norms. And that should give us the answer, right? So the L2 norm of vector u, the square root of what is the norm of this vector? What is the length?
1 squared plus 0 squared plus minus squared plus 2 squared, 9.
Yeah, or if I have the square root, then it's 3.
3. Yeah.
And if we take vector v, then it would be
square root of 3. Yeah.
Yeah. So which one is larger? 3 or square root of 3?
3, yeah.
3 is larger, right? So that means that vector u is longer than vector v, right? Everyone agrees? Right.
Yeah.
So that's sorry, that should also be the right answer. Let me mark it. All right. Now, the last question. Euclidean distance between vectors u and v is 20. Is that so? How do we compute Euclidean distance between two vectors? Yeah. So it's essentially we need to compare the we need to look at the difference between these vectors, and we take we compare the lengths, we compute the length of the distance between two vectors, right? And that will be the length of the difference between two vectors, right? Which will be the distance. Logically, right? So if this is if this is one vector, this is the other vector, right? U and v, then this is distance between them, well, the difference between them, and the length of this vector is what we call the distance, right? And what is this distance in this case? The Euclidean distance. And here, if we compute the distance, the difference between u and v, it will be 1 minus 0 is 1, so 1 squared plus 0 minus 1 is minus 1, so again 1 squared, minus 2 minus 1 is minus 3.
Minus 9 is 9,
Yeah.
So 2 plus 9 again, it's 20.
Yeah.
So it's 20, square root,
under
root 20.
Yeah.
And
So the distance is, the square of the distance is 20, but the distance itself is square root of 20, right? So that's why this statement is not correct, right? Because we need to take the square root, right? So 20 is there, but 20 is the square of the distance. And the distance itself is square root of 20. All right. Okay, so I hope that this is clear now. Let's see. Yeah, we didn't get any more responses. Are there any questions, anything that anyone wants to discuss in more detail? Let's see that other questions were generally all right. Okay. If there are no more questions, then let's move on with the first practical exercise. So now I hope you refreshed all these concepts of vectors, distances, angles, and so on and so forth. So let's do a short practical exercise in Python. Let me know if you are familiar with Python and if you worked with Jupyter notebooks or Google Colab notebooks, right, with something like this, if you worked before or not. Let me know in the chat if you've seen this before or if it's all new. Okay. Yeah. Let's see. So as expected, some people worked with it already. For some people, that's relatively new, but that's good because then now it's a nice opportunity to learn it, to get to know it in more detail. Just again to be on the safe side, I'll explain what it is. Right, this is the notebook. Notebook is a very interactive way of coding, right? There you have this is a Google Colab notebook, so it's kind of a Google Doc kind of notebook that you can edit online, you can share with other people. The notebook has different cells. The cells can be text cells, and where different formatting is supported. So I can write Markdown, I can write LaTeX if I want to write formulas, can include pictures, right? Then it renders it like this. But there is also code, right? And we can write Python code here and we can run it either by clicking this play button or by selecting the cell and hitting Shift Enter at the same time, right? And we'll run the cell. Okay, and in this notebook, it's I'm going to share it with you right now. Let me create the link and I'll send it to you. Okay, so now you have the link. So you should be able to open this, right? And it will automatically create kind of a copy of this notebook for you, right? So don't be afraid to edit it, right? You will be editing your own copy. And this notebook is about vectors, right? And it's about maybe a little bit fun application of vectors, right? Namely the color vectors. If you worked with colors on a computer, then you know that one way of encoding colors is using this RGB code, right? That basically you specify, right? It turns out that every color can be specified by saying how much red, how much green, and how much blue you take, right? So essentially, every color is a three-dimensional vector, right? Because every color you can define by three numbers. Every color is a set of three numbers. The first coordinate is the amount of red, the second is the amount of green, the third is the amount of blue, right? So you can see colors as vectors. And you can see, if you imagine colors like this, like vectors, then immediately you can do all kinds of things that you can do with vectors with colors, right? You can compute the distance between two colors. You can add colors up, you can compute the difference between colors, you can compute dot products between colors, and so on and so forth, right? You can plot colors in a three-dimensional space as points in 3D space, and so on and so forth, right? And this is what this exercise is about, right? So we will see how to perform all these basic operations with vectors in Python using this NumPy library, which is the standard library for working with linear algebra objects, right? With this fun application, all right? Some cells here are already pre-filled, so just run them. The first cells, they are about getting the data, reading the data into this RGB format. So don't think too much about it. Just run it, and it will convert the data from this hexamal format into this RGB code, right? And then starting from this second section about plotting the data, right? This is where you can start working with this, right? You will need to complete some code. Normally now, I think if you enable here the AI assistants, the code will be completed almost automatically, right? But anyways, try to, even if you get these suggestions, right, try to understand how it's written, what it's doing. Right, and yeah, you'll have a sequence of questions about different operations that you can do on these scalar vectors. Your task will be to fill in the missing parts of the code and see what it does. All right. Can everyone access this notebook? Yeah, perfect. Now, so that it's a bit more interactive, I see that we are with 8. So let me create 2 breakout rooms so that we can do this exercise in smaller groups. All right. Perfect. So I'll open the rooms right now. You can join within the groups. You can discuss the exercise. The idea is that you do it together. Maybe some of you can share the screen. Yeah. Also, of course, feel free to just chat. If you haven't met before, it's also nice. Right, and let's spend maybe 15-20 minutes on this exercise. We'll see how it goes, and then we'll discuss your findings, right? And I'll give you some time to work in groups, and I'll be visiting both rooms to in case you have any questions. Okay. So I'm opening the rooms right now. Please join them and have fun.
Hello, please, is the session over? Hello?
Yeah, sorry, I was muted. Yeah, you are supposed to see the invitation to join a breakout room where you will be working on this notebook together with your peers, right? So you must see now a pop-up window, right, from Zoom that asks you if you want to join. So click on join, and then you'll be there. Right. So how was it? You can let me know in the chat if it was too easy, too difficult, if it was fun, and how much you've done, if you managed to look through all of it, or if there are any questions. I asked, seemed that no one had any issues, but just in case. Right. So how was it? Too easy, boring, too difficult? No one? Have you managed to implement something there, or is there any problems? Let's not spend too much time on it, so I'll just show you some interesting, in my opinion, some interesting aspects or cool things, fun things. But I hope that you all find the math between it pretty easy, right? It's just about the basic operations with vectors, with three-dimensional vectors, right? So something small and easy, right? In case you are not really familiar with Python or haven't used Python very much, then hopefully that's a good warm-up. Otherwise, that should have been pretty straightforward, right? The point of this exercise, once again, is that a vector is that every color can be represented as a three-dimensional vector. And these vectors are points in three-dimensional space, right? We can plot them, right? If we plot them, we'll have a cloud of points like this. And what is interesting here is that you can notice that points are grouped together by color, right? So similar colors are close to each other in space, and colors that are very different, they're far away from each other, right? So we have some area with blues, area with yellows, area with some almost black colors, green colors, and so on and so forth, right? Again, very, very logical why this happens, but kind of cool to see, right? And then you can, you can compute distance between colors, right? Because, for example, this is a distance between the color red and dark red, right? Something like 97. And the distance between red and blue is indeed higher number, right? You can find, using these distances, you can find the colors which are most similar to a given color. So for example, if this is a grayish color that I invented, right, we can look up the closest colors from our database, right, by just looking for what's called in machine learning nearest neighbors, right, the vectors which have the smallest distance to the current one, right, and these turn out to be the closest vectors to this color, right? So you see that these colors are indeed somewhat similar, especially the top nearest neighbors, right? And then you can, of course, add up or subtract one color from another, right? And it's also kind of, it seems to me that it's cool to see that it's a really very basic math operation, but then it also makes sense kind of in the real world, right? If you add up red and blue, then you'll get purple, which is correct, right? If you've painted, then you know that that's the case, right? If you subtract red from brown, you get green, right? Because green and red give you brown. So I think it's pretty fun, right? How this very, very simple operations gets this meaning, right? If you look at it and if you look at this application. Okay. Just to make sure, are there any questions? Is there anything that's not clear? in this notebook? If not, let's do one more exercise. So these were vectors, but there was another concept that you've learned about in the lecture, and that was a hyperplane, right? What is a hyperplane? Does anyone remember? What is a hyperplane? How is a hyperplane defined? Anyone? Let's see the message from Alexander, who messaged us the way of the equation that defines a hyperplane. Let's see what it means, right? So if we are in a 2D space, right? If we are in a 2D space with two axes, x1 and x2, what is a hyperplane in such a 2D space? Yeah, hyperplane is just a line, right? I'm gonna plot it. Yeah, this is a hyperplane in a 2D space. It's just a line. And if we are in a 3D space, so if we have x1, x2, and x3 now, how will a hyperplane look like? Yeah, in a 3D space, a hyperplane will be a plane indeed. Let's see, here is the plane. I don't want it to have any filling. Yeah. Here is it, our hyperplane in a 2D space. And in high dimension, a hyperplane will be always a subspace of a dimension that is smaller by 1, right? So in a 2D space, hyperplane is a one-dimensional subspace, so a line. In a 3D space, a hyperplane is a two-dimensional subspace. In 4D, it will be a three-dimensional subspace, and so on and so forth, right? So let's, for the purpose of visualization, right, let's stay in 3D, right? More I can't really draw. And then, what Alexandra told us is in the chat, right, is how this hyperplane, or in this case, in the 3D case, plane is defined, right? Turns out that the equation of a hyperplane is something like this, right? We can define it with weights. W2 times x2 plus W3 times x3 plus some intercept equals 0, right? That's the equation of the hyperplane. Okay. This is hyperplane. And yeah, we can write it down in a more compact way using the dot product notation, right? The dot product of the vector W times point X plus B is 0, right? So any point X that satisfies this equation lies on a hyperplane. So this equation defines the hyperplane, right? The vector W is a vector of these coefficients, W1, W2, W3. And together with this intercept B, this vector and these coefficients b, this intercept b, define the hyperplane. All right. What do we know about these vector w? What is so special about these vectors? Which property does this vector w? Does anyone remember? Yeah, Max says that vector w is orthogonal to other vectors. Namely, which other vectors? Is orthogonal to anything that lies on this hyperplane, right? So if I plot it, right? Let me just draw it. I'll take my tablet. If I take any vector that lies on the hyperplane, right, my vector w will be orthogonal to it, right? This is vector w, and it's orthogonal to anything that lies on the hyperplane. All right. Why is that so? Can anyone explain? Because that's not obvious, right? We said that this equation defines this hyperplane. That's clear, right? But why is that so that this vector w is suddenly orthogonal to anything that lies on the hyperplane, right? So if I call this green vector, let me call this vector S, right? What is the case is that this vector w is orthogonal to any vector S that lies on the hyperplane, yeah, or any S on the hyperplane. The question is why? Can anyone explain why this is the case? Does anyone know? How come that this vector is orthogonal or normal? Let's see, I'll give you a hint, all right? And then maybe you'll be able to prove this yourself, okay? So what we need to show, right? If I want to prove you that vector w that defines the hyperplane is indeed orthogonal to this hyperplane. So we need to prove that no matter which vector S on this hyperplane I take, my vector w will be orthogonal to it, right? That would mean that w is orthogonal to everything on this hyperplane. So I drew vector S like this, kind of floating, right, in on this hyperplane. Let's try to express this vector S in a different way, right? Let me consider two vectors like this. Let's call them vector u and vector v, right? They are. All right. Can we express S in terms of these two vectors, u and v? Any idea? Vector S that lies on the hyperplane, right? It's kind of this floating vector, and then I have two standards, let's say, vectors that start from origin, right, and So basically 2 points on this hyperplane, V and U. How are they related, the 3 of them? Vector S. Would you agree if I say that vector S is simply the difference between vector V and U? Right? Good. People agree. Right. So if this is a difference, now let's take a look. What we are interested in is a dot product between W, our normal vector, the vector that defines a hyperplane, and this random vector S that we chose, right? So now we established that vector S can be represented as the difference between V and U, okay? So the dot product, yeah, I can just use this fact inside the dot product. And now, since we have this property of a dot product that it's linear, right? The dot product between vector W and the difference between V and U is simply the difference of 2 dot products, right? Like this. Okay? Right, I just employed this property of the dot product. Now, what can we say about the dot products between vector W and V and the dot product between vector W and U? Do we know something about this? What is this difference? We want to show that this difference, since we want to prove that W is indeed orthogonal to the hyperplane, what we want to show is that this dot product is 0, right? So we've used the fact that S can be represented as a difference of 2 vectors, V and U, right? So now this product is a difference of these 2 dot products. Ideally, we want to show that this is 0. The question is why, right? Any thoughts? What do we know about the points U and V? About these points. Point U, vector, or point U and V. They both lie on this hyperplane, right? U and V, they are lying on the hyperplane. That means that just like any other points that lie on the hyperplane, that means that they satisfy this equation, right? That means that the dot product between W and U plus B is 0, and the dot product between W and V plus B is 0. Agreed? Because points U and V belong to this hyperplane, they satisfy the equation that defines it. And what does it mean for our difference? It means that the dot product between W and V is minus B, right? And the one between W and U is also minus B. So the difference between the two is 0. And this is how we prove, right, that whatever vector on the hyperplane we choose, the vector W, the one that defines this hyperplane, is orthogonal to this vector because the dot product between them is 0. And that means that this vector, the weight vector W, is indeed orthogonal to the entire hyperplane. All right? Is that clear? Yeah, good. Max agrees. That's good. Great. Do you remember in which context we discussed hyperplanes in the lecture? Why are they interesting to us? Yeah, linear models. There was this example, right, where we were interested in basically creating a classifier, right? So suppose again in a 2D case, right? You might have some examples. Let me draw it, right? You have some points that belong to one class, the green class, and you have some other points that belong to a different class, the red one, and you might want to train a model that distinguishes between the two classes. And the simplest model, right, it will learn kind of the line, the border, the separating line, and tells you everything that's on top belongs to one class, everything that's below belongs to the other class, right? And that's that line, right, is called the separating hyperplane, right? Let me draw this line, right? So we might learn something like this, right? Something like this. So again, in this 2D example, we learn line. In high dimensions, right, we'll learn a separating hyperplane, right? In 3D, that will be a plane, 4D, 3D subspace, and so on and so forth, right? So this is a separating hyperplane, right? This separating hyperplane is defined by some equation. Again, Wx plus b is 0, right? This v and b, these coefficients, this normal vector to this hyperplane and the intercept b, you get, they are learned from, or by the ML model, right? This you learn somehow. And then when a new point arrives, right? If you want to use this classifier to classify new points, right? Suppose you have a new point, and it's somewhere here, right? It's a new point, X. How do you use this model to classify this new point? How do you decide which class does it belong to according to your model? Yeah. So Max says whatever is positive or negative, and what should be positive or negative exactly. Yeah, so in this case, how would we classify this point X? how would our model classify this point? Is it the green class or the red class? Yeah, it's classified as green. And why is that so? Yeah, it's classified indeed as a positive class, as a green class, right? Because X is above the hyperplane, right? And this is what we see visually. But if we want to implement this, right, we will not do this visually. We will not perform this check visually. We will take a look at the dot product between our weight vector W, X, B, right? And this will be larger than 0, right? And this is why this point will be classified as the one that belongs to the positive class, or the green on this picture, right? If we take something here, right, some other points, some other point here, let's call this point Y, right? And point Y will be classified as red because it's below the hyperplane, right? And for this point, if we plug it into this equation of the hyperplane that we learned by with some machine learning model, right, the result will be negative, right? So again, this is how this simple primitive classifier works, right? You learn some hyperplane, meaning that you learn the weight vector W and the intercept B that define the hyperplane, and then whenever a new point appears, right, you just plug it into this equation, see if you get a number, a positive number, you say it's a positive class. If it's a negative number, you say that it's a negative class, right? And if you're unlucky and you get something that's lying exactly on the hyperplane, right? If you get exactly 0, then you say you don't know really, right? Or you can classify it randomly. Okay. So now I see that we are at time. Next time we start with doing some practical Python exercise on this, exactly on this hyperplane, right? So we will use some ML model to learn this hyperplane, and we'll implement this classification by hand, right, from scratch, rather than using the built-in method. All right. Are there any questions? Any doubts? Anything that's still unclear from the lecture? If not, then thank you very much for joining, and have a good week. Enjoy the lecture on Thursday, and I'm looking forward to seeing you in a week.
Thank you.